In this video, I'm going to go through an example of finding the Taylor polynomial for a complicated looking function. And I'm going to do that by taking advantage of a couple of Taylor polynomials that are familiar and using the two facts mentioned in the previous video about Taylor polynomial tricks. So the one that we're going to be doing here is the Taylor polynomial for the function e to the 1 minus x squared, all divided by 5 plus 3x, and the polynomial I want is of degree 3 and expanded about x equals 0. So you might call this a Maclaurin polynomial instead of a Taylor polynomial. Okay, so first let's start off just writing down f of x. The first thing I want to point out is that when I have e to the 1 minus x squared, e to the 1 multiplied by e to the minus x squared, that e to the 1 is just a constant. I can factor it out in front. So I'm left with e to the minus x squared. And that is going to be divided by 5 plus 3x. But, well, let's see. I'm going to move this down. Well, the functions that I'm going to use that I have familiar Taylor polynomials for are e to the x, and that one has a Taylor polynomial 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed. And I'm going to stop at x cubed for sure because I only want a degree 3 approximation to this function. So the pieces probably need at most a degree 3 approximation. And then I also want to use 1 over 1 minus x, which may not be as obvious, but it is, and I'll point out why in a second. So we have 1 plus x squared plus x cubed. And again, I'm going to stop at the cube. And now if you look at this expression here, we can rewrite f as e to the minus x squared divided by, and now what I'm going to do is, if I factor out a 5, we get a 1 plus 3 over 5 x, but I recognize now that I've got a denominator there that's very close to 1 over 1 minus x. So I'm going to put this over here. Actually, take this 2. And then this one is just multiplying it. And then I have a 1 there. And now I'm actually going to rewrite the thing in the denominator. Instead of plus 3 over 5, I'm going to make that a minus sign and move this over a little bit and put a minus in front with a bracket. And hopefully now, written like that, you can see why 1 over 1 minus x is going to be useful. Specifically, this function is actually 1 over 1 minus, and then some function plugged in place of the x here. And this x had to be small, and when x is small, what I'm plugging in, minus 3/5 x, will also be small. So we will have a good place to use this Taylor polynomial as part of estimating f of x with a Taylor polynomial. Okay, so here we have over 5 here, and then the e to the minus x squared, and I can write it like that actually. Why don't we do that? So like this, and then 1 over 1 minus 3 over 5x. And so writing that with a Taylor polynomial, I'm going to say that's approximately equal to e over 5. And now e to the minus x squared, I'll use this Taylor polynomial to approximate that. So if I plug in minus x squared in place of x, I get 1 plus minus x squared plus 1/2 minus x squared all squared plus 1 over 3 factorial minus x squared cubed. And then we're going to multiply that by the Taylor polynomial for this guy, which is 1 plus minus 3 over 5x plus minus 3 over 5x squared plus minus 3 over 5x cubed. Okay, So now a quick trick, or a trick to simplify or quicken calculating the lowest power terms up until the point where first let me actually simplify those. So here I have an approximately equal to, and that's actually referring to both the f and the right hand side because those are both equal to each other. But now I could think of this, I'll just put an approximate. This approximate is to the original function. It's equal to exactly this because I'm just going to rearrange some of the things inside those brackets. Okay, so what I get in the brackets, I get 1 minus x squared plus 1/2 x to the 4. And you'll notice this term here is going to be an x to the 6. And it's going to get multiplied by a 1, an x squared, an x cubed. There's no way that x to the 6 multiplied by any of these is going to be relevant for us here because we're only going to degree 3. So I could have left this out of my original approximation. I didn't need that. So I'll leave it out here. And now it's a good thing I'm using approximately because this is equal to neither of the above expressions. Okay, so there's our x to the 4. And we're going to stop there. And now we're going to multiply that by 1 minus 3/5x plus 9/25x squared. And now the question is, do I need this x cubed? Well, that x cubed is going to be able to get multiplied by a 1. So I will need this one in getting up to degree 3 because I want to include every possible degree 3 term when I multiply these two expansions. And so if I omitted this one, I'd be missing a piece of my coefficient to the x cubed term. Okay, so now I need that. So I'm going to add that in, and it has a minus sign in front because it's a negative cubed. And then 3 to the 3 is 27, and 5 to the 3 is 125 x cubed. Okay, so now, and I'll keep the almost equal to, even though this is going to be exactly equal to that one, because I'm just going to rearrange the parts. So now, what I'm going to do is I'm going to, instead of doing some systematic multiplication of, let's say, the first by all of these, and then the second by all of these, and so on, I'm going to ask the question, from this product, how can I get a constant term? And there's only one constant term that appears. There's a 1 here, and it has to multiply a non-x term. So these are the only ones that are going to give me a constant term, so I get a 1. Next, I want to know plus something, and I'll put this way over here, probably further than I need. I'll scrunch it down after. So now how can I get x terms out of this? Well, there's no way an x squared or an x to the 4 can multiply any of these terms to give me a linear term. So the only thing I can do is multiply this 1 by an x term. And so I get minus 3/5 over here, and no other sources of x's, so I can actually bring that guy all the way back. And now I can ask the same thing for x squareds. So how can I get x squared terms? Well, I can multiply this 1 by the 9/25. So I have a 9/25 here. But there's other ways. I can multiply the minus x squared by the 1. So I have a minus 1 times x squared. And then there's no other ways of getting x squared because the next term here is x to the 4, and that power is already too big to get an x squared. So I'll close the bracket and I'll go x squared. And finally, I want to know how many ways are there to get an x cubed. And let's list all those out. So we have 1. This 1 could multiply this x cubed. So we have minus 27/125. And what other ways do we have? We have an x squared that could multiply an x. So there's a minus and a minus, that gives me a plus, and the coefficient is 3/5. And that is going to give, that's the only x cubes. The next term over is x to the 4, too big. So we just have x cubed now, Oh, and I guess I misspoke. This inequality, this almost equals, does apply to both the previous line and all the ones above, because we've gotten rid of some powers, right? Because we're going to have a power of x to the 4, an x to the 5, and an x to the 6th, and an x to the 7 that we're omitting because those are beyond our desired degree 3. Okay, so now we have just a couple calculations to do. E over 5, 1 minus 3 over 5x plus 9 over 25 minus 25 over 25 is, let's go for a minus sign there, minus 16 over 25x squared. And then here we have plus, and then if we multiply the bottom by 25, we get 125. So we have 75 in the numerator. So 75 minus 27, 27 is bringing down by 20, gives you 50. 55 and minus 7 is 48. So here we have 48 divided by 125, and that's multiplied by x cubed. So once we multiply this e over 5 through, then we have our Taylor polynomial of degree 3 written out with each of the coefficients. Okay, so once you know a Taylor polynomial like this, if you wanted to quickly calculate something like the third derivative at 0, there's an easy way to do this. Obviously, if you've calculated derivatives already to get the Taylor polynomial, then you can just plug it in. But we didn't do that. We used this shortcut. And what that means is that we can actually just use the Taylor polynomial to figure out what the derivative is at the origin, or in this case, the third derivative. And so remember that the coefficients, or the terms in a Taylor polynomial, are going to be f nth derivative evaluated at 0 divided by n factorial, x to the n. So if we're looking for the third derivative at 0, that means we're going to choose n equal 3, so we'll have f triple prime of 0, x to the 3 over 3 factorial. So in this expansion over here, the degree 3 term is e over 5 times 48 over 125 x cubed. And so for this to be a term of this form, I have to be able to equate f triple prime of 0 over 3 factorial to e over 5 times 48 over 125. And that means the third derivative at 0 is going to be equal to 3 factorial times e times 48 all over 625. Now, it's tempting to think maybe we can cancel, but 625 is actually 5 times 5 times 5 times 5. And so the only prime factor of 625 is 5. And that does not appear in any of these terms in the numerator. So we could multiply these out, but I don't see much reason to do that. So I'm going to leave that as my answer. And so that is how we use known Taylor polynomials to estimate the Taylor polynomial of a composite function, where we have both a product of two functions and, in both cases, a composition. And then we also can extract the derivatives of the function evaluated at 0 fairly easily.